going back to Explained, where we like grab those like super complex topics that are, floating around out there and kind of break them down into something that, you can actually use.
Yeah, you can think of it as your cheat sheet to understanding the world, one deep dive at a time.
And today we're tackling something that is like incredibly important and often just completely mysterious. The way that data actually travels across networks. The thing that lets you watch cat videos and you join video calls and pretty much run your entire digital life.
Yeah, it's the invisible infrastructure that makes the internet possible. And, while most of us just take it for granted, there's a whole lot of fascinating stuff happening behind the scenes.
Okay, so let's unpack this. Have you ever stopped mid-click and wondered, how does this information actually get from point A to point B? How does that actually happen?
Right.
So it all starts with this thing called the data link layer, which is the packaging and delivery service of the network world.
Yeah, exactly. It's the layer that's responsible for taking, those chunks of data from the internet layer above and preparing them for transmission across the physical medium, whether that's a cable, a wireless signal, or even fiber optic lines.
So it's like putting those cat videos and emails into envelopes and making sure they're addressed correctly and then sending them off on their little journey.
Precisely. And the data link layer doesn't just package the data, it also controls access to the shared medium. So think of it as a traffic cop at a busy intersection, making sure data from different devices doesn't collide and cause a digital traffic jam.
So it prevents those data packets from getting into a fender bender. It's pretty important, I would say.
Absolutely. And in some cases, the data link layer even provides reliable delivery between adjacent nodes, ensuring that if a frame gets lost or damaged in transit, it's retransmitted.
Now, I've heard of TCP, which also guarantees delivery. Is that doing the same thing?
Yeah, that's a great question. So TCP operates at a higher layer, the transport layer, and it guarantees end-to-end delivery. Think of it as a registered letter with tracking information. The data link layer's reliability, on the other hand, is only between devices that are directly connected, so two computers on the same network. It's more like handing something directly to your neighbor.
So it's like local delivery service versus a global shipping company.
Exactly. Now, besides these key functions, the data link layer also offers other helpful services like flow control, which ensures that a sender doesn't overwhelm a receiver with too much data too quickly. It's like pacing yourself at a buffet so you don't get a digital stomachache.
That's a great analogy. I like that.
And there's error detection and correction, where the receiver can either flag errors for retransmission or in some cases even correct those minor errors on the fly. It's like having a built-in spell checker for your data.
So the data link layer is like a multitasking ninja, ensuring smooth and reliable data transmission.
Absolutely. But to truly understand how those ones and zeros travel across those physical media, we need to peek into the world of the physical layer. The foundation upon which all this digital magic rests.
Okay, now we're getting down to the nitty-gritty. What exactly happens at the physical layer?
This is where data transforms into signals ready to traverse those physical cables or wireless channels. And it involves encoding and modulation, which basically means converting those digital bits into a form that can be transmitted over different media, like copper wires, coaxial cables, or those super fast fiber optic strands.
So it's like translating digital language into something that those physical materials can actually understand.
Precisely. Now, signal strength isn't limitless. It weakens as it travels, which is called attenuation. And this is where the choice of physical media becomes really crucial.
Yeah, because different materials have different strengths and weaknesses.
Exactly. Each medium has its own bandwidth limitations, which affects the amount of data it can carry effectively. Think of it like a highway. A wider highway can handle more cars at faster speeds compared to a narrow, winding road.
So fiber optic cables are like those super highways of the data world.
You got it. They have incredibly low attenuation, meaning signals can travel those vast distances with minimal loss of strength. And their high bandwidth capacity, well, let's just say they make copper wires look like dirt roads.
Yeah, that explains why fiber optic connections are so much faster. So you've got your DSL, your cable, and your fiber when it comes to internet connections. I'm kind of curious, what type of internet connection do you have at home? Let us know down in the comments.
Oh, good question. Yeah, I'm fortunate enough to have fiber. The speed and reliability are unmatched. But regardless of whether you have DSL, cable, or fiber, it's incredible how these wired access networks connect us to this vast digital world.
Yeah, it's like having a direct pipeline to all the information and entertainment the internet has to offer.
Definitely.
And speaking of access networks, Let's talk about those multiple devices all trying to share the same transmission medium. How do we prevent them from creating a digital demolition derby?
Right, yeah. That's where multiple access protocols come into play. They're like the rules of the road, ensuring a fair and efficient sharing of that transmission medium, whether it's a cable or a wireless channel.
So they're like traffic lights and roundabouts, but for data.
Precisely. The biggest challenge here is avoiding collisions, those data pileups that occur when multiple devices transmit simultaneously.
Right, because those garbled signals would be about as useful as a scrambled Rubik's Cube.
Exactly. Now, there are three main types of multiple access protocols: channel partitioning, random access, and taking turns.
Okay, let's break those down. What's channel partitioning all about?
So with channel partitioning, the transmission medium is divided into smaller pieces like time slots or frequency bands. Each device gets its own exclusive slice of the pie, preventing any chance of collisions.
So it's like having dedicated lanes on a highway.
Exactly. Two common examples of this are TDMA, which stands for Time Division Multiple Access, and FDMA, which stands for Frequency Division Multiple Access.
So with the TDMA, each device gets its own time slot to transmit, and with FDMA, it gets its own dedicated frequency band. Seems pretty organized.
It is. It's a neat and organized approach, but it can be a bit inefficient if some devices have more data to send than others.
Right, because those unused time slots or frequency bands just go to waste.
Right.
So that's where random access comes in.
Precisely. Random access protocols allow devices to transmit whenever they have data, but they listen to the channel first. If it's busy, they wait their turn. But if a collision does occur, they back off for a random amount of time before trying again.
So it's a bit like a polite mosh pit. Everyone's eager to jump in, but they try to avoid crashing into each other.
Exactly. The most well-known example of this is CSMAD, or Carrier Sense Multiple Access with Collision Detection, which is used in traditional Ethernet networks.
So that's what's happening behind the scenes when I'm like browsing the internet or downloading files.
Yeah.
Pretty cool.
Yeah, it is. Now, while random access is great at low traffic volumes, it can get bogged down with collisions when things get busy. And that's where the taking turns protocols come in. They aim to combine the best of both worlds, ensuring fairness and avoiding collisions, while allowing devices with more data to send to hold the floor for longer.
So it's like an orderly queue, but with VIP access for those with more to say?
Exactly. Two common taking turns protocols are polling and token passing.
Polling sounds familiar. What's that all about?
So with polling, there's a central controller that goes around asking each device if it has data to send.
So it's like a teacher calling on students in a classroom.
Precisely. It's a simple and reliable approach, often used with less sophisticated devices, but it can create overhead and latency, especially with many devices.
And what about token passing? How does that work?
Imagine a digital token being passed around a circle. Only the device holding the token can transmit. Once it's done, it passes the token to the next device in line.
So it's like a game of hot potato, but for data. That's a fun way to think about it. And each of these protocols has its pros and cons, right?
Absolutely. The choice of which one to use depends on the specific network environment and requirements. It's all about finding that right balance between efficiency, fairness, and reliability. Make sure you follow Explained for more deep dives into these fascinating topics.
And speaking of specific network environments, let's
Yeah.
zoom in on local area networks, or LANs. These are the networks within our homes, offices, and schools. And when it comes to wired LANs, the undisputed champion is Ethernet.
Ah, yes, Ethernet. It's simple, affordable, and it's kept pace with the ever-increasing demands for speed, evolving from a humble 10 millidps to a blistering 400 Gbps and beyond.
It's quite a speed boost. What makes Ethernet so successful?
At the heart of Ethernet is its frame structure. Remember those frames we discussed earlier? Well, Ethernet has its own specific format for packaging data.
So it's like a specialized container for LAN traffic.
Precisely. Each Ethernet frame has a header with the destination and source MFI addresses, a type field that indicates the higher layer protocol, and a data payload, which is the actual data being transmitted.
And let's not forget the CRC, the error checking code that ensures data integrity.
Absolutely. The CRC is like a digital checksum, making sure that the data arrives intact. Now, one of the key characteristics of Ethernet is its connectionless nature. There's no handshaking or setup required between sending and receiving devices. It's a simple send and hope for the best approach.
So it's a bit like sending a postcard.
Yeah.
You just write the address, slap on a stamp, and drop it in the mailbox.
A good analogy. But this simplicity comes at a price. Ethernet is also unreliable. The receiving device doesn't send back any acknowledgments or error messages. If a frame gets lost, it's gone.
So it's a bit of a gamble. But how is data loss handled then?
That's where higher layer protocols like TCP come in. If an application requires reliable data transfer, it relies on TCP to handle retransmissions and error recovery.
So TCP is like the insurance policy for those critical data packets.
Exactly. It adds that extra layer of protection, ensuring that important data gets through, even if some Ethernet frames go astray.
So Ethernet focuses on speed and simplicity, leaving the heavy lifting of reliability to those higher layer protocols.
Precisely. It's a division of labor that's proven incredibly successful. Now, in the early days of Ethernet, coaxial cables and hubs were the norm. But these days, it's all about switches.
Switches. I know those are important, but I'm a bit fuzzy on the details. Can you explain what they do?
Sure, so switches are intelligent devices that direct traffic within a network. Unlike hubs, which simply repeat incoming signals on all ports, switches make forwarding decisions based on MS addresses.
So they're like traffic cops directing traffic to the correct destination.
A perfect analogy. Each switch has a switch table, a database that maps MNS addresses to the corresponding port on the switch. So when a switch receives a frame, it looks up the destination MACE address in its table and forwards the frame only to the port connected to that device.
That's pretty efficient. No more wasted bandwidth sending data to devices that don't need it.
Exactly. This selective forwarding eliminates collisions, which were a major bottleneck with those old hubs.
Right, because with a hub, all devices were essentially sharing the same transmission medium, leading to those digital fender benders we talked about earlier.
Precisely. Switches create separate collision domains for each port, allowing multiple devices to transmit simultaneously without interference.
So switches are like creating individual lanes for each device, preventing those data pileups.
Exactly. And here's the really cool part. Switches are self-learning. They build their switch tables dynamically by observing traffic.
Self-learning. That sounds impressive. How do they do that?
It's actually quite simple. When a switch receives a frame, it learns the source MA address and the port it came from, and it adds this information to its switch table.
So it's like a detective gathering clues and building a case file. Over time, the switch builds a comprehensive map of the network.
Exactly. But what happens if a switch receives a frame with a destination MA address it hasn't learned yet?
That's a good question. Does it just give up?
Not quite. In that case, the switch resorts to flooding. It sends the frame out on all ports except the one it came from, hoping that the intended recipient is listening somewhere.
So it's a bit like shouting out in a crowded room.
Exactly. It's not the most efficient approach, but it's a necessary fallback mechanism. And as the switch learns more, MSC addresses the amount of flooding decreases.
So over time, the switch becomes more efficient and intelligent.
Precisely. And this self-learning ability makes switches incredibly easy to deploy. You just plug them in and they figure everything out on their own.
That's the beauty of plug-and-play technology. No complex configuration required.
Exactly. And to make things even better, switches also offer full duplex communication, which means devices can send and receive data simultaneously.
So it's like having a two-way conversation instead of a walkie-talkie exchange.
A perfect analogy. And this full duplex capability further enhances the performance of Ethernet networks.
Switches are truly amazing devices. They've revolutionized LANs, making them faster, more efficient, and easier to manage. It's remarkable how such a simple concept can have such a profound impact.
Absolutely. They've become the backbone of modern wired networks, connecting everything from computers and printers to servers and storage devices. Imagine you have a large network with hundreds of devices, all connected to the same physical switches.
Okay, I'm picturing a massive web of cables and blinking lights.
Now imagine you want to divide this network into smaller logical groups, perhaps based on departments, work groups, or security levels.
So it's like creating virtual walls within the physical network.
Exactly. And that's precisely what VLANs allow you to do. They segment a physical LAN into multiple logical LANs, enhancing security, efficiency, and manageability.
So it's like having separate apartments within a single building, each with its own set of rules and access controls.
A great analogy. Each VLAN acts as its own independent network, even though they share the same physical infrastructure.
That's pretty cool. But how are VLANs actually created? Do you need special hardware?
Not necessarily. Most modern switches support VLAN functionality. There are two main types of VLANs, port-based and tag-based.
Okay, let's start with port-based VLANs. How do they work?
With port-based VLANs, you assign specific ports on a switch to a particular VLAN. So any device connected to those ports automatically becomes a member of that VLAN.
So it's like assigning rooms to specific tenants in that apartment building.
Exactly. And this way, traffic within a VLAN is isolated from other VLANs. Devices in VLAN 1 can only communicate with other devices in VLAN 1, and so on.
That sounds like a great way to improve security.
It is. You can prevent unauthorized access to sensitive data by segregating devices into different VLANs. And it also helps with traffic management. By dividing the network into smaller broadcast domains, you reduce the amount of unnecessary traffic flooding the entire network.
Right, because those broadcast messages like ARP requests are only sent within the corresponding VLAN.
Precisely. And port-based VLANs are relatively easy to configure. You just go into the switch's management interface and assign ports to VLANs.
Sounds straightforward enough.
It is. But port-based VLANs have some limitations. What if a device needs to be a member of multiple VLANs?
Right, that could be a problem if someone moves to a different department or needs access to resources in another work group.
Exactly. And that's where tag-based VLANs come in. Instead of assigning VLAN membership based on physical ports, tag-based VLANs add a special tag to each Ethernet frame.
So it's like adding a label to a package indicating its destination.
A perfect analogy. This tag, defined by the 802.1q standard, contains the VLAN ID, which tells switches how to handle the frame.
So even if devices are connected to different physical ports, they can still be members of the same VLAN if their frames have the same VLAN tag.
Exactly. And this flexibility is what makes tag-based VLANs so powerful. You can have devices spread across multiple switches and still group them into logical networks based on those tags.
So it's like having a virtual address that overrides the physical location.
Precisely. And to connect switches together in a VLAN environment, we use special ports called trunk ports.
Trunk ports, are those like the main highways connecting different parts of the city?
You could say that. Trunk ports carry traffic for multiple VLANs. They encapsulate those tagged Ethernet frames within a special protocol header so that switches can distinguish between different VLANs.
It's like having multiple lanes on that highway, each carrying traffic for a different VLAN.
Exactly. And this way, devices in different VLANs can communicate with each other as if they were on separate physical networks, even though they're sharing the same physical cables.
VLANs are a pretty ingenious solution. They add a whole new dimension to network management.
Absolutely. They provide flexibility, security, and efficiency, making them a cornerstone of modern LAN design.
And speaking of large-scale networks, let's take a step further and explore the fascinating world of data centers. These behemoth facilities are like the engine rooms of the internet, housing rows upon rows of servers that handle everything from website hosting to cloud computing.
It's amazing to think that so much of our digital world relies on these massive data centers.
It really is. Designing data center networks must be incredibly complex.
It is. You're dealing with tens or even hundreds of thousands of servers all interconnected and working together to deliver those services we rely on.
That sounds like a logistical nightmare. How do you even begin to design a network on that scale?
Well, data center networks typically follow a layered architecture. You have server racks, each containing dozens of individual servers.
Like those towering cabinets packed with blinking lights that you see in movies.
Exactly. And at the top of each rack, you have a top-of-rack switch, or TOR switch.
So it's like having a local traffic cop for each server rack.
Precisely. The TOR switch connects all the servers within its rack and provides high-speed links to the next layer of switches, which are called Tier 2 switches.
So it's like a hierarchical chain of command with each layer handling increasingly larger amounts of traffic.
Exactly. And finally, you have border riders, which connect the data center to the outside world, the internet.
So it's like a gateway between the internal network and the vast digital landscape.
Precisely. And this layered architecture allows for efficient traffic flow and scalability. You can add more server racks and switches as needed without disrupting the overall network.
It's like building a city with a well-planned road network. But with data centers, it's not just about connecting devices, right?
Right. It's also about balancing the workload across those servers to ensure optimal performance.
Because if one server gets overloaded, it could slow down the entire system, like a traffic jam in a key intersection.
Exactly. And that's where load balancing comes in. It distributes incoming traffic across multiple servers, preventing any single server from becoming a bottleneck.
So it's like having multiple cashiers at a supermarket to prevent long queues.
Precisely. And load balancing can be implemented at different layers of the network, from the application layer down to the network layer.
So it's a multifaceted approach to optimizing performance. Fascinating. When it comes to the actual layout of the data center network, I've heard of something called the fat tree topology. What's that all about?
The fat tree topology is a popular design that mimics the structure of a tree. Imagine a tree with multiple levels of branches, all connected to a central trunk.
Oh, okay, I'm visualizing it.
In a fat tree topology, server racks are connected to the lowest level of branches. Then those branches connect to higher level switches, which eventually converge at the core Tier 1 switches, forming the trunk of the tree.
So it's like a network that mimics the structure of a tree with data flowing up and down the branches.
Precisely. And this design offers several advantages. It provides multiple paths between any two servers, increasing throughput and resilience.
So even if one link fails, there are alternative routes for the data to flow, like detours around a road closure.
Exactly. And the fat tree topology also makes it easy to add more servers and switches without disrupting the overall network structure.
It sounds like a very scalable and robust design. But as data centers continue to grow in size and complexity, are there any challenges that arise?
You're right to think about that. Traditional switching technologies like STP, the spanning tree protocol, which prevents loops in a network, can reach their limits in these massive environments.
We talked about STP earlier in the context of Ethernet networks. How does it fall short in data centers?
So STP was designed for smaller networks where it prevents loops by blocking redundant links. But in massive data centers where redundancy is crucial for resilience, STP can be too slow to respond to failures.
So it's like having a traffic cop who takes forever to redirect traffic after an accident.
A good analogy. And that's why data center networks are moving towards more advanced switching and routing techniques like TRLL and SPB, which provide faster convergence and better utilization of available bandwidth.
So it's a constant evolution driven by the need for ever-increasing speed, capacity, and reliability.
Yeah.
That's amazing.
It is. Data center networks are at the forefront of networking innovation, constantly pushing the boundaries of what's possible. Now, speaking of key players in the networking world, let's compare and contrast routers and switches. They often get lumped together, but they have distinct roles and operate at different layers of the network.
Oh, yeah, I'm ready to dive into that. What are their similarities?
Both routers and switches are store and forward devices. This means they receive a data packet or frame, store it briefly in memory, and then forward it to the appropriate destination.
So they're both like mail sorting facilities, receiving, processing, and redirecting those digital letters.
A good analogy. And both routers and switches maintain forwarding tables, which they use to make those forwarding decisions.
So they both have a kind of internal map of the network.
Exactly. But here's where their paths diverge. Routers are network layer devices operating at layer 3 of the OSI model. They examine the network layer headers of data packets, typically IP headers, to determine the destination network.
So they're like those long-haul truckers transporting data across vast distances from one network to another.
Precisely. And switches, on the other hand, are link layer devices operating at layer 2. They focus on the MSC addresses of devices within the same local network.
So they're like those local delivery drivers, ensuring that packages reach the correct house within a neighborhood.
A perfect analogy. And the way they build their forwarding tables also differs. Routers use routing protocols like RIP, OSPF, or BGP to exchange routing information with other routers and build a comprehensive map of the internetwork.
So they're constantly chatting with each other, sharing intel about the best routes to reach different destinations.
Precisely. And when a router receives a packet, it uses a technique called longest prefix matching to find the most specific route in its forwarding table.
Longest prefix matching. That sounds like a mouthful.
It's actually quite intuitive. Think of it as finding the most specific address in a phone book. If you're looking for someone named John Smith, you want the entry with the most complete address, including street name, city, and zip code.
Ah, so you want the most precise match, the most detailed route.
Exactly. And routers excel at this. They can handle complex network topologies and efficiently route traffic across vast distances.
Impressive. So routers are the long-distance champions.
hmm
But what about switches? How do they build their forwarding tables?
Switches take a more hands-on approach. They learn about the network by observing traffic. Remember that self-learning ability we discussed earlier?
Right. They sniff out MC addresses and build their switch tables dynamically.
Precisely. And when a switch receives a frame, it simply looks up the destination MC address in its table and forwards the frame to the corresponding port.
So it's a very localized approach. They're not concerned with routing traffic across different networks, just within their own little domain.
Exactly. And this makes switches incredibly efficient for local communication. They don't have to worry about complex routing algorithms or exchanging information with other devices. They just focus on getting those frames to their destination as quickly as possible.
So routers are the strategists, the big picture thinkers, while switches are the tacticians, the on-the-ground operators.
A perfect analogy. Each has its strengths and weaknesses, making them ideal for different networking scenarios.
So when would you choose a router over a switch, or vice versa?
Well, if you need to connect multiple networks together, perhaps a home network to the internet or different departments within a large organization, then a router is your go-to
Because
device.
they're designed to handle those inter-network communications.
Exactly. But if you're just connecting devices within a single local network, then a switch is the more efficient and cost-effective choice.
Because they excel at those localized high-speed connections.
Precisely. And often you'll find both routers and switches working together in a network. The router handles the external connections while the switches handle the internal traffic.
It's a beautiful symphony of networking devices, each playing its part to create the seamless digital experiences we enjoy.
Absolutely. It's a testament to the ingenuity of network engineers who've developed these technologies and protocols that make our modern world tick.
Well, we've covered a lot of ground in this deep dive so far. From the fundamental layers of the network model to the intricacies of routers, switches, and even those massive data centers, it's been quite a journey.
It has. We've explored the invisible infrastructure that makes our digital lives possible. And in part two, we're going to delve even deeper into that world of data transmission.
Okay.
We'll be exploring error detection and correction, the evolution of Ethernet, and the fascinating world of switching techniques.
Sounds good.
So let's kick things off with error detection and correction. These mechanisms are essential for ensuring the reliability of data transmission, especially over less reliable media like wireless networks, where signals are more prone to interference.
Yeah, because those Wi-Fi signals can be a little flaky sometimes, especially if you're far from the router or like there are walls and other obstacles in the way.
Absolutely. So whether it's detecting errors with CRCs or correcting them with error-correcting codes, these techniques work tirelessly behind the scenes to keep our digital world running smoothly.
It's like having a safety net for our data, making sure those cat videos and important work documents arrive safe and sound.
Precisely. Now let's shift gears a bit and talk about a technology that's near and dear to my heart, Ethernet. It's the backbone of most local networks, quietly connecting our devices and enabling us to share those precious cat videos and get work done.
I'm all ears. Ethernet seems so ubiquitous these days, it's easy to take it for granted.
Yeah.
I'm curious about its history and how it's evolved over time.
Well, Ethernet has an interesting origin story. It was actually inspired by a wireless network.
Oh, really?
Yeah. In the early 1970s, an engineer named Robert Metcalf was working at Xerox PRC, and he had this vision of connecting computers within a building using coaxial cables. His inspiration came from the Aloha Network, a wireless packet radio network developed at the University of Hawaii.
So the idea for wired Ethernet came from a wireless network. That's pretty ironic.
It is, but it highlights how innovation often builds upon existing ideas, even those that seem unrelated at first glance.
That's true. So how fast was that first version of Ethernet?
It ran at a speed of 2.94 millipedes, which might seem incredibly slow by today's standards, but at the time it was revolutionary. It enabled computers to share files and resources at speeds that were just unheard of.
Yeah. I bet people's minds were blown.
Yeah.
What happened next?
As technology advanced, Ethernet kept pace. We saw the introduction of 10 millipedes Ethernet, which became the standard for homes and offices for years.
Right. I remember those RJ45 connectors and Cat5 cables. They were everywhere.
Exactly. Then came 100 MLPs fast Ethernet, followed by gigabit Ethernet, which was 1,000 times faster than the original Ethernet. And the speeds just kept increasing, 10 gigabit Ethernet, 40 gigabit, and now we're even talking about 100 gigabit Ethernet and beyond.
It's incredible how quickly Ethernet has evolved to meet that growing demand for speed and bandwidth.
It really is. And each new iteration brought with it new challenges and opportunities for innovation, from the physical layer to the protocols that govern its operation.
So it's not just about like cranking up the speed, it's about optimizing that entire ecosystem to handle that increased traffic.
Precisely. And one of the most remarkable things about Ethernet is that it's managed to maintain backward compatibility throughout its evolution.
Backward compatibility, what does that mean?
It means that newer, faster Ethernet devices can still communicate with older devices, albeit at the slower speed of the older device. It's like having a conversation between someone speaking a modern dialect and someone speaking an ancient version of the same language. They can still understand each other, even though the vocabulary and grammar might be a bit different.
That's a great analogy. So I can plug my brand new laptop into an older network and it'll still work.
Exactly. That backward compatibility has been crucial for the widespread adoption of Ethernet. It's allowed networks to evolve gradually without requiring companies and individuals to constantly replace all their existing equipment.
Yeah, it's like upgrading a city's road network without having to demolish all the buildings. Makes a lot of sense.
Exactly. And this adaptability is one of the key reasons Ethernet has remained the dominant local area networking technology for over 4 decades.
It's a true testament to its design and its ability to keep pace with the ever-increasing demands of the digital world.
Absolutely. Now let's talk about another important aspect of networking switching techniques. This is all about directing traffic within a network, making sure data packets get to their destination quickly and efficiently.
So it's like being a digital air traffic controller guiding those data planes through the network airspace.
I like that analogy. And just like air traffic control switching involves making those real-time decisions based on a variety of factors, like network congestion, available bandwidth, and priority levels. And there are different switching techniques, each with its own strengths and weaknesses.
Let's start with the basics. How does circuit switching work?
Imagine you're making a phone call. In a circuit switch network, a dedicated path or circuit is established between your phone and the recipient's phone.
So it's like having a private line, a direct connection just for that call.
Exactly. And this circuit remains in place for the duration of the call, ensuring a constant and reliable connection with a fixed amount of bandwidth.
That sounds pretty straightforward. Why don't we use circuit switching for everything?
Well, circuit switching is great for real-time applications like voice calls, where you need a continuous flow of data. But it can be inefficient for data networks, where traffic is often bursty and unpredictable. If the connection is idle for long periods, that dedicated circuit is just sitting there unused, like reserving a lane on a highway for a single car, even if it's parked.
That makes sense. So that's why we use packet switching for most data networks.
Precisely. In packet switching, data is divided into small units called packets. Each packet has a header containing routing information, like the destination address.
So it's like sending a letter, but dividing it into multiple pages, each with its own address label.
A perfect analogy. And these packets are sent independently over the network. They don't all have to follow the same path, and they might even arrive at the destination out of order.
So it's like a treasure hunt with each packet finding its own way to the destination.
That's fascinating. It is. And at the destination, those packets are reassembled in the correct order, like putting the pages of that letter back together.
But if they're all traveling independently, how do those packets know where to go?
Each packet's header contains the destination address, and routers along the way use this information to forward the packet to the next hop, the next router closer to its final destination. Think of it like a relay race, with each router passing the packet to the next runner.
That's a great way to visualize it. So unlike circuit switching, packet switching doesn't require a dedicated circuit the whole time.
Exactly. Packets from different sources can share the same physical links, which makes much more efficient use of network resources. It's like having multiple cars sharing the same highway lane as long as they're all heading in the same general direction.
So that's why packet switching is the foundation of the internet. It allows all those emails, videos, and web pages to zip around the world so efficiently.
Precisely. Now, there are different types of packet switching. One important distinction is between datagram packet switching and virtual circuit packet switching.
Okay, I'm intrigued. What's the difference?
So in datagram packet switching, each packet is treated independently. Routers make forwarding decisions based only on the packet's destination address. It's like sending each page of that letter as a separate postcard. They're all going to the same place, but there's no guarantee they'll arrive in order or even at the same time.
So it's a more flexible but less predictable approach.
Exactly.
Yeah.
And that's fine for many applications, but what if you need a more reliable and predictable connection, especially for real-time applications like video calls?
Right, because with video calls, you need the data to arrive in order and with minimal delay to avoid those frustrating pauses and glitches.
Precisely. That's where virtual circuit packet switching comes in. It establishes a virtual connection between the source and destination before any data is transmitted. It's like reserving a dedicated lane on that highway even though multiple cars might be sharing it. This virtual circuit ensures that packets arrive in order and with the speed and predictability that real-time applications demand.
So it's like a blend of the best aspects of circuit switching and packet switching.
Exactly. It provides the flexibility and efficiency of packet switching with the reliability and predictability of circuit switching.
That's a clever solution. It's amazing to see how these different switching techniques have evolved to meet the diverse demands of data communication.
It is. And as networks continue to grow and become even more complex, we're seeing even more sophisticated switching techniques emerge, like multi-protocol label switching or MPLS. It's a bit more complex, but essentially it adds a label to each packet, similar to a tag which routers use to make forwarding decisions. This labeling scheme allows for faster routing and more granular control over traffic flows.
So it's like having a priority label on a package, ensuring it gets expedited delivery.
A perfect analogy. MPLS is widely used in large-scale networks to optimize performance and manage quality of service. And that's just one example of how networking technologies are constantly evolving to meet the ever-increasing demands of our digital world.
This is all so fascinating. It makes you appreciate how much complexity and innovation goes into something we often take for granted.
Absolutely.
Right.
And there's so much more to explore. In part three, we'll delve into the world of wireless networks, security protocols, and the future of networking.
Sounds exciting.
Yeah, it'll be fun. So let's dive into the world of wireless networks.
Okay.
These have become so essential, for our modern, always connected
I know,
lifestyles.
right? Think about it. You can access the internet from like practically anywhere these days. Your home, your office, coffee shops, even on airplanes. It's amazing.
It is.
Yeah. But I got to admit, the whole concept of like wireless communication still feels kind of like magic to me. How does data actually travel through the air?
Well, it all starts with radio waves.
Yeah.
So Wi-Fi uses radio waves to transmit data wirelessly between devices and a central access point, like your Wi-Fi router at home.
So it's like those old school radio broadcasts, but instead of music and voices, we're sending data packets.
Exactly. But instead of broadcasting to like a wide area, Wi-Fi focuses those radio waves into a more directed beam, creating a localized network.
So it's like having a private conversation using radio waves, rather than shouting to like the entire neighborhood.
Hey, perfect analogy. Now, just like with wired networks, Wi-Fi uses different frequencies to transmit data. The most common frequencies are 2.4 gigahertz and 5 gigahertz.
Yeah, I've seen those options in my Wi-Fi settings. What's the difference between them?
So 2.4 gigahertz is kind of like a well-traveled road, It's been around longer and it
Mhm.
has a wider range, but it can get crowded with signals from other devices, like microwaves, Bluetooth devices, even baby monitors.
So that's why my Wi-Fi sometimes slows down when I'm using the microwave.
Quite possibly.
Yeah.
5 gigahertz, on the other hand, is like a newer highway, with more lanes and less traffic.
Yeah.
It offers faster speeds and less interference, but its range is shorter.
So it's like a trade-off between speed and coverage.
Exactly. And choosing the right frequency really depends on your specific needs and environment. If you need to cover a large area, 2.4 gigahertz might be the better option. But if you prioritize speed and reliability, especially for things like streaming video or online gaming, then 5 gigahertz is the way to go.
Good to know. Now, we've talked about MC addresses before, those unique identifiers for like every device. Do they play a role in wireless networks as well?
Absolutely. MC addresses are crucial for both wired and wireless networking. They allow devices to identify each other and communicate directly within a network.
Okay, so let me see if I got this straight. When I connect my phone to my Wi-Fi at home, my phone's MC address is used to establish that connection with the router.
Exactly. The router uses your phone's MC address to identify it and assign it an IP address, which is
Okay.
like a temporary address for your device while it's connected to the network.
So it's like checking into a hotel. Your MC address is your identity, and the IP address is the room number you're assigned for your stay.
A perfect analogy. And once your phone has an IP address, it can communicate with other devices on the network and access the internet.
That's pretty cool. Now, security is always a big concern with wireless networks. I've heard of things like WPA2 and WPA3. Can you explain what those are and how they keep our data safe?
Absolutely. Security is paramount in the wireless world. So WPA2 and WPA3 are encryption protocols that scramble the data being transmitted between your devices and the router, making it unintelligible to anyone who might be eavesdropping.
So it's like putting your data into a secret code that only your devices and the router have the key to decipher.
Exactly. WPA2 has been the standard for many years, but WPA3 is the newer, more robust protocol that offers stronger encryption and better protection against attacks.
So if my router supports WPA3, I should definitely be using that.
Absolutely. Always opt for the highest level of security available. And speaking of security, it's crucial to choose strong, unique passwords for your Wi-Fi network and all your devices.
Right, because weak passwords are like leaving the door to your digital house wide open.
Exactly. Now, beyond the security protocols built into Wi-Fi, there are other things you can do to kind of enhance your network security. For example, enabling a firewall on your router adds like an extra layer of protection, blocking unauthorized access to your network from the outside world.
So it's like having a security guard at the entrance to your network screening incoming traffic for suspicious activity.
Precisely. And keeping your router's firmware up to date is crucial as well. Firmware updates often include security patches that address newly discovered vulnerabilities.
So it's like installing the latest security system updates on your digital house.
Exactly. Taking these proactive steps can significantly enhance the security of your wireless network and protect your sensitive data.
That's great advice. It's so easy to just connect to Wi-Fi and not think about the security implications. But it's important to be mindful of those risks and take steps to mitigate them.
It is. Now, looking ahead, the future of networking is full of exciting possibilities. We're seeing a convergence of wired and wireless technologies with even faster Wi-Fi standards like Wi-Fi 6 and Wi-Fi 7 on the horizon.
I've heard about Wi-Fi 6. It promises even faster speeds and better performance, right?
Exactly. Wi-Fi 6 is designed to handle the growing number of devices and the increasing demand for bandwidth in our homes and workplaces. It's like upgrading the roads and infrastructure to accommodate more traffic and faster vehicles.
So we can expect even smoother streaming, faster downloads, and lag-free gaming.
Precisely. And beyond Wi-Fi, there's a lot of buzz around 5G cellular technology and its potential to revolutionize not just mobile communication, but also home internet access.
5G is super fast,
Yeah.
right? I've heard it can even rival or surpass the speeds of some wired connections.
That's right. 5G offers incredible speeds and low latency, which opens up all sorts of possibilities for new applications and services.
It's exciting to think about what the future holds for networking. Who knows what innovations we'll see in the coming years?
It really is. The world of networking is constantly evolving, driven by our insatiable appetite for speed connectivity and new ways to communicate and share information. It's a testament to human ingenuity and our collective desire to connect with each other and the world around us.
It's been an incredible journey exploring the world of networking with you. We've gone from the fundamental building blocks of data transmission to those cutting-edge technologies that are shaping the future of how we connect.
I've enjoyed it immensely. It's been a pleasure sharing this knowledge and hopefully sparking some curiosity along the way.
Well, this wraps up our deep dive into the fascinating world of networking. We hope you've learned something new and gained a better appreciation for the complex systems that make our digital lives possible. Make sure you follow Explained for more deep dives into all sorts of fascinating topics. And be sure to let us know what you'd like us to explore next. Until next time, happy networking.